All right, welcome everybody. I think it's time to get started. So I have a great talk lined up today by Dr. Mohammad Shafiq, who's a professor at New York University, Abu Dhabi. And the talk is on energy efficiency and security for TinyML and EdgeAI, a cross-layer approach. First up, I'd like to introduce some of our strategic partners who have helped by sponsoring this series of talks. So we have Aeon Devices, ARM, DeepLight, Edge Impulse, which is where I work, EMSA, PhotoHub, Greenwave Technologies, Gravetti Incorporated, HOTG, Imagimob, Itemis, Clicker Tech, Latent AI, Maxim Integrated, Micro AI, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renesas, Rexen, SAP, Seed, SensiML, ST, Stream Analyze, SynSense, and Sentient. And if you're interested in sponsoring the TinyML talks, please don't hesitate to reach out to olga@tinyml.org for some more information. So I also want to talk a bit about the upcoming TinyML Summit 2022, for which we have the tagline, Miniature Dreams Can Come True. So this event is going to be from March 28th to 30th, 2022 at Hyatt Regency San Francisco Airport. And the Best Product of the Year and Best Innovation of the Year awards are currently open for nomination. So please go in there and nominate your favorite products and innovations. It's going to be a great event. I'm going to be there. Hope to meet you all. Concurrently, we'll be hosting the TinyML Research Symposium 2022, which is March 28th. So both of the links on here, you can head over there and get some more information. So once again, if you're interested in sponsoring any of these events, drop an email to sponsorships@tinyml.org. We have coming up on the second next installment of the TinyML Trailblazers series, which is very exciting. So this showcases some success stories in the world of TinyML. And this edition, which is presented by Chris Warren, features Joel Rubino, who's the CEO and co-founder of Cartesium. That's going to be live online February 2nd, 2022, which is tomorrow at 8 a.m. PST. So you can use the QR code there to register. You can also participate in the TinyML community by joining one of our online or in-person communities. So Meetup, it's kind of amazing. We started out, with one meetup in Silicon Valley that I helped start. And we now have 8,000 members in 42 groups in 33 different countries. So chances are there's going to be a local meetup that's close to you. You can register there and find them. And there are in-person meetups going on currently as well, COVID permitting. We also have an online community on LinkedIn. So we've got a few thousand members and followers there who are there to chat about TinyML. So please head to either of those and join in. So our YouTube channel has become one of the coolest resources in embedded machine learning. We have 347 videos of content like the talk that we're about to see today. It's been accumulating for a couple of years now. We've got about 6,000 subscribers, loads of views, loads of really, really high quality talks. So come along and subscribe to the YouTube channel and you'll get an update every time we publish one of these talks. This talk will be published in the couple of days afterwards. Our next talk in this series is on Tuesday, February 8th, so that's next week, and it's from Stefano Cardario, who's the Director of Product Management from the IoT group at ARM. So his talk is on Get Ahead of the Curve, Develop Software in the Cloud for Ethos U55 and Cortex M55 processors. So that should be super exciting. Starts at 8 a.m. Pacific, as always. And if you have an idea for a talk, we'd love to hear from you. So just drop us a line at talks@tinyml.org if you are interested. So now it's my pleasure to introduce Dr. Mohammad Shafiq. So Shafiq is an associate professor in the Division of Engineering at NYU Abu Dhabi, UAE, and a global network associate professor in the Tandon School of Engineering. He's received his PhD in computer science from Karlsruhe Institute of Technology in Germany. From September 2016 to August 2020, he was a full professor of computer architecture and robust energy efficient technologies at the Institute of Computer Engineering, Vienna University of Technology. Dr. Shafiq has received ACM SIGDA Outstanding New Faculty Award, AI 2000 Most Influential Scholar Award in 2020, a Spire Award for Research Excellence, and multiple Best Paper Awards and nominations at flagship conferences. So without further ado, Shafiq, I'll let you take it away.
Perfect. Thanks, Daniel, for the kind introduction, and welcome everyone to the talk. So I'll start with this thing, that why machine learning and AI has been getting so much of attention now, and is it really the true boom or not? So for ages, humans have ruled the world, and nations have dominated and got supremacy because of multiple reasons. Earlier age, it was manpower, their skill set. In the later age of technology, we had the fuel, industrial technology, economic politics, and all those kind of stuff, But lately, if you see that from this last decade, we are witnessing a new era, and transgressing into this new era, which is the age of data and AI. So data is the new fuel. So whoever holds the most of the data can then, for example, really mine and get the information out of it, can dominate certain policies, can play a certain role in politics. Innovation in technology is also the new politics nowadays. You can see there is a nationwide race in the dominance of AI, and not only AI, but also multiple other disruptive technologies like quantum computing, 6G, and those kind of stuff. And sooner or later, you will see that these kind of technologies are gonna overlap to some extent. For example, we have quantum machine learning, ramping up, and then, doing smart intelligence and scalable intelligence over 6G, those kind of stuff you will see coming, on the landscape. So in today's talk, what I'm going to show you that what is TinyML and EdgeAI, there are certain differences, and they constitute one of the, kind of the major area in the horizon of AI. And the applications are numerous, and you can keep on imagining as many use cases as possible as you can, where any form of smartness or intelligence would be required from your underlying system that we typically use in our daily life. Then later I'll introduce you our cross-layer design flow, where I'll show you that in order to enable efficient TinyML and EdgeAI with high performance, energy efficiency, as well as security, we need to engage both hardware and software, layers of the system stack. And I'll pitch towards the end. I'll pitch a couple of the open research challenges and directions where people are moving forward, where we are going to look forward, and then hopefully conclude the talk with some key takeaway messages. Now, TinyML and EdgeAI, what are the unique features, first of all, different from the regular AI or machine learning that we see in the cloud? So first of all, the primary thing is that we would like to enable on-device data analytics, predictions, and intelligence at extremely low power budgets, which basically means that we have some kind of overlap between the certain properties of an embedded system, which would be, for example, a very small computing device under certain limited resources in form of power, for example, in form of memory, in form of compute capabilities, certain real-time constraints, also safety and security and reliability constraints. For example, if you're going to put these kind of systems in some critical industry, smart factories, or in autonomous vehicles. And also certain constraints on the ML algorithm, because you would like to have the highest performance if possible at the least power budgets that you can spend on. So most of these TinyML and EdgeAI systems are on-device ML under stringent design constraints, stringent online constraints. And I'll show you towards the end that it's not only inference, it's also stepping in the domain of learning, on-the-fly learning also. Most of these systems are always on use cases, or most of the time on use cases. And these devices are battery powered or even self-powered devices kind of concept, where the power is harvested again during the operations. scalable to trillions of sensors. We are talking about connecting all these smart devices in the world of Internet of Things, and it's eventually an Internet of smart or AI things. Now, what's the difference between a regular AI working in a cloud versus EdgeAI and versus TinyML? So that basically the primary difference comes from the constraints that we define onto the system and the system or device that we are using, and eventually that dictates the model that we can load on top of that. So cloud AI, for example, we are typically using for training, high-end learning, and even very massive kind of parallelized inference, which is also inference on a service, for example, as a service that we provide typically on high-end GPUs like A100, working on terabytes of memory, having tens of to hundreds of terabytes of storage. And the application, as I said, is model training, big data analytics, and all those kind of stuff. Now, when we talk about edge AI, edge AI and TinyML primarily move towards the embedded AI kind of thing. So now, what is the class of your embedded device? That dictates how stringent is your design constraints. If your device is like an ADAS, like automotive, this advanced driver assistance system, or it could be a mobile device doing some app with some high-end intelligence. It could be a robot, for example, which is working on the field and interacting with people. Those kind of systems can have embedded GPUs, can have embedded neural processing units, which can have a few hundred of megabytes to a couple of gigabytes of memory and storage. And again, this is a lot of embedded processing, and these models can be even much more complex. They can be multi-headed DNN models. They can be multiple different type of DNNs, or heterogeneous DNN models kind of stuff, as well as there is a need for contour learning. And then TinyML is a niche, but having a wide range of applications, where we started with microcontroller-based intelligence. And now, it's also moving towards or moving forward with small neural processing units, doing this intelligence for you at very, very, tiny system, which can be tens to hundreds of kilobytes of memory with maybe 1 megabyte of the total storage or 2 megabytes of total storage. And this is primarily in-sensor or near-sensor intelligence that we are talking about. And in-sensor intelligence is great. Anyway, application to preserve the privacy of many, many applications. You can think of ranging from sensors deployed for predictive maintenance to all the way up to wearables. So edge AI is like really tight constraints, but TinyML is like extreme constraints. And I'll show you that many of the optimization and design principles that we follow for designing TinyML edge AI systems, may benefit from each other. There is a lot of synergy and overlap between those kind of principles. But the constraint definition inside the design flow is primarily that dictates the final model and final hardware that you can deploy. Now, applications are, as I said, is a wide range of applications. Smart cyber physical systems, ranging from smart automobiles to robotics to smart factories, cyber physical system factories, smart homes, smart grids, healthcare. So numerous applications, subsystems of these applications. All those kind of things. You can put intelligence each and every place, ranging from sensor to all the way up to the brain of a robot. And when we generate data from trillions of sensors in a connected world, efficiently inferring knowledge from this big data is primarily and driving prediction. AI and ML is the primary tool that we are gonna use effectively. The challenges are also, a lot, because when we talk about critical systems or smart cyber physical kind of systems, having critical sensors deployed, robustness, both in terms of reliability and security, is one of the primary goals. And on the other hand, you want performance both in terms of high accuracy as well as in terms of real timeliness and low latency, and high throughput is also extremely important. Your car is driving, you don't want it to crash, and you want to react in time and do like this. But there are a lot of other soft requirements which are important, like safety, privacy, interoperability, adaptability, programmability, and all those kind of stuff that we care for. Now, I give you a little bit in-depth idea of what is the gravity of the complexity challenge here. For example, if you look at this, ResNet 50 was one of the famous models, for vision, and then we saw that there are models like Megatron, GPT, which are used for NLP, and then there is a vision transfer kind of stuff. So just to give you an idea, that Megatron, for example, was more than 2000x complex than ResNet 50. It required 512 V100 GPUs to train, and then when we look at the trend than the GPT-3 was, for example, 90,000x, compared to ResNet. So even if you get these models trained using very big cloud, and you want a very small, tiny device to serve your purpose, and in an EdgeAI kind of, for example, setting, even then putting this kind of network in a small setting is very, very difficult. And I'll show you that if we just realize autonomous driving kind of use cases, you don't need one model. You might have multiple models, you might have multi-headed models and things like that. So the challenging question that we pose here is that if we have a huge amount of data and robustness and energy efficiency are the primary constraints, what kind of things that we have to consider when designing TinyML and EdgeAI kind of systems? What is the range of the constraints that we care for eventually? Just to give you an idea, compared with the efficiency of the modern system, your human brain with the full level of intelligence that we can think of, requires only 20 watts. While a similar level of intelligence you might have seen, big servers playing chess or those kind of stuff, require, megawatts of power. So we're talking about an efficiency gain of 1,000 to 100,000x. And now tomorrow you want to have a tiny robot sitting in front of you and playing thing really live and continually learning, on the fly. That should happen, in few watts, or ideally even below that, because a human brain does a lot of other functionality, not only the strategy and the vision. So this was the performance and power challenge. What is the security challenge? Many of these devices, when we put in real world autonomous systems, they open up a new surface of vulnerabilities. Which means that, welcoming message to a lot of attackers, and again, also challenges on the safety validation, formal verification, and all those kind of stuff. So you can see that there have been a lot of news feeds about the accidents of these autonomous vehicles, and I'm not going to details, but there are a lot of other kind of things. So one of the Chinese company, for example, they bought Tesla, and they did some black box attacks on the autopilot of the Tesla. And this is one of the first, black box attack that you can see on the screen, where they showed some random noise on a picture, to the automotive, and suddenly the environmental control system was activated, and it thought it's a rain, and then the wiper started moving. They did another test where they showed that if we put 3 patches on the road, somehow we can fool the lane detection or lane departure kind of system, So now this guy has switched on the autopilot mode of the Tesla. And, when the 3 patches which were randomly placed, were visualized, then, suddenly the car thought that there is a lane departure, and then, it departed the lane. So a lot of times these kind of things can be faked, can be put through adversary, and these are called the environmental perturbations. And there is a wide range of environmental perturbations that people have done in the attacks of these kind of systems. Now imagine that you are going to put this system in some windmill, or in some small robot, or in other kind of stuff, and so it's a wide range of attack surface that you're offering to the hackers. So summarizing the challenges, first lie in terms of complexity, but that's not only the compute challenge, that's a big memory challenge, because when we are mapping these deep neural networks on the neural processing unit, for example, which are very tiny, your full neural network does not map or fit into that chip. So you are typically processing layer by layer or part of the layer, and then shuttling the data between the on-chip memory and off-chip memory. So controlling these memory transfers and exploiting the extensive reuse which could be available, for example, in your design, or you can actually use reuse maximization as a design constraint or design parameter, that could actually help you to cut down significantly the cost of your memory transfers, memory energy. Reliability, I did not go into details, but when we are fabricating these chips in nanometer regime, then there are a lot of reliability threats. For example, there could be permanent faults, there could be transient errors, there could be aging-related issues, there could be variability. So those kind of things are also extremely important. And when we have tight safety constraints and certification issues, then we need to cover up with all these things. So for example, in automotive systems, you might need to put 2 chips, in order to make sure that you have dual model redundancy and make sure that such kind of errors are not, hampering your system. And in security, I already told you that there could be other kind of attacks that could be data poisoning or adversarial attacks that you are doing on the system. Now, having said that, there is a lot of effort which is going on in parallel by the community, and this is great. There are a lot of cross-layer design flows which are being developed jointly by the community. There are a lot of features which are available in the modern tool chains like TensorFlow Lite and MicroTVM, and you can just take a model and try to compress that model and try to fit into your device settings. Then there is also a growing trend of putting hardware accelerators, which can be, for example, 4x4 NPU or 8x8 small NPU, which is accelerating the MAC computations, vector operations, and those kind of stuff. This could be another interesting thing for you to look into. And then, the another emerging trend is, of course, employing neural architecture search under hardware constraints, which basically mean that you can give your memory constraints, you can give your maximum flop constraints, you can even give the energy constraints of system, and then you can output automatically search model configuration through these NAS. Or you can take a model and then try to do aggressively prune and quantize to compress the model and fit it in your system. For example, you can go up to 4-bit, or even you can go up to binary network. But then you have to see that how much accuracy you are losing in general. And now there are modern trends which are combining multiple of these optimizations in one synergistic framework. Having said that, when we started doing this research, several years ago in our lab, we thought that we should first understand what is the, really the nature of the problem, what is the seriousness of the problem. So we started with the software-based implementations, analyze the data flows, reuse potential. We developed different analysis tools, to automatically analyze that how this data is going to be, for example, shuttled between different memory components. Then we started developing naturally the hardware accelerators, because that's where my background was. So we started developing some dedicated pipelines and memory hierarchies and on-chip memory structures for accelerating these deep learning engines. And then in the later phases, what we start looking into is hardware-aware NAS kind of optimizations, where we are integrating certain hardware constraints in the automated neural architectural search. We are looking into different types of networks, not only the convolutional, but also, for example, the capsule networks and spiking networks. So neuromorphic, for example, is a great growing area where, there is a great potential of exploiting the event-based nature of spiking networks to cut down significantly the power and energy. And towards that, we are working on the Lohi chip to build certain use cases for autonomous vehicles. Then in-memory computing, I mean, a lot of people are working worldwide in this area because, memory, there are hypotheses the brain itself is just a memory, and if you can do a lot of computation and inferring it to the memory, then you can save a lot of power and energy. So ReRAM based architectures, where people do some kind of analog computing, can also be one way to look at this. And then there is mixed CMOS kind of designs, where you have a memory of ReRAM, you have neural accelerators, you have dense copper wires connecting them, building 3D chips like that. This is one way to move forward. So there is no single silver bullet, to cope with this challenge. If we are really planning to have a high-end brain working at below 1 watt of budget, for example, in a robotic, head, we need multiple of these kind of things. So I call it as a multi-dimensional research challenge, where technology, hardware architectures, memory experts, and intelligent software design and optimization flow have to be integrated, synergistically. We have looked into these problems individually. We are extensively working with my team and try to integrate as much as possible, and then let's see, what comes out of that. The security research that we are looking into is primarily in the scope of advanced cyber-physical systems like autonomous vehicles or robotics, systems, where the decision making and suggestion, recommendations, for example, are done by the deep neural engines. So we are looking into, for example, two main type of attacks. One is the backdooring, which is done during the training time, and there are different type of backdooring. We are looking into different formal aspects. We're looking into the latent variable spaces and all those kind of stuff, and try to identify if there is a unique feature, space or representation that we can formulate to avoid the backdoors. Then there are adversarial attacks that are done on the fly during inference. For example, when your TinyML and EdgeAI system is being deployed in the final product, then how to avoid adversaries to attack that model and how to robustify your network. Privacy attacks, model stealing attacks is another important aspect, because we spent millions of dollars in order to develop an IP. Nobody should be able to steal that IP, and people have shown that they not only steal the IP, but they can even reverse engineer the data set which was used to train that IP, or at least build a proxy data set or proxy model out of it. Again, a lot of other threats that can, so these are the threats that typically exist at the application of the system level, but there are a lot of other conventional threats which exist at the hardware level. For example, inserting Trojans so that your system can behave abrupt whenever the adversary wants it to be, or there could be side channel attacks to learn some unique things from your machine learning IP. So there is a wide range of stuff. Multiple of the team members are working in different aspects of these security things. Having said that, I would like to present a quick overview of our cross-layer framework. I'll spend a bit more time in explaining that, and then afterwards I can give you a little bit of sneak preview of different achievements that we have done as part of this framework. The first thing that we do is training. We are extensively looking into how to make the training efficient. If we can learn certain things during the training and can be used to robustify the network, or for example, try to learn analytical models that can be fed into the hardware awareness framework and things like this. Once we do that, there are two different ways of designing neural networks, and we are trying both, and we are hoping that we can come up with some integrated solution to that. Currently, this is underway. One is that we train a network and try to do aggressive model compression. I'll show you some of the results that how we can achieve very, very aggressive model compression and quantizations. And another way that what we do is that we give these as a constraint and employ some kind of hardware awareness. And for that, we are looking into genetic algorithms that can give us a better set of Pareto optimal design points. And I'll show you that even for one of the healthcare applications, we have achieved a significant savings in terms of hardware when outputting a certain neural network model. Once we have it, we do some very interesting things which are called approximations. We can approximate the data, we can approximate the computations. For example, 3 multiplied by 3 is not 9, rather 7. We can tolerate these small errors due to the inherent resilience of certain neuron operations, and then we can get extra 20 to 30% of, for example, energy savings out of it. What we have done towards this thing, we have also designed some self-healing approximations which primarily follow the principle of mirror approximation design, which means that one multiplier generates positive error, other can generate the negative error. And when we're doing the MAC operation and accumulation, then the positive and negative error can cancel out. And towards the end of the complete processing, we might have either no error or very, very few error. So we have even demonstrated a fully curable neural accelerator, where all the errors can be nullified. And then we also do some kind of, on-chip and off-chip memory optimizations, and I'll show you a little bit details of that. Give you a little bit idea how much savings we're talking about here. Model compression can give you up to, 190x, depending upon, of course, the model, depending upon, how much retraining we want to invest and how much accuracy loss we can tolerate. The curable approximation can give you 1.5x energy saving at absolutely no accuracy loss. And I'll show you that if you start tolerating a little bit loss, then you might go up to 2x of energy savings. With DRAM energy savings, we have demonstrated close to half of the memory that accesses that we can save by efficiently exploiting the reuse in input feature maps, output feature maps, and even the activation function values. Once we have an optimized design, you can see is that we then output a very compact model, a very optimized model. Then we study its resilience. We study its resilience in terms of different type of faults. There could be like permanent faults. For example, some of the cells in your memory can be faulty, or some of the processing elements can have faults and things like this. So this work is done with one of the industrial partners. We looked into, for example, how to increase the yield of chips without doing extensive retraining by just efficiently remapping, our deep neural network on some of the chips, and this can significantly increase the yield of the final system. So there are a lot of different type of threads ranging from soft errors, aging to all the this, and for every type of thread we have a certain optimized solution. The output of this step is an optimized and resilient deep neural network. Then what we do is that we do some runtime security attacks and try to understand the vulnerabilities that we can close. And towards this end, we also do some kind of formal analysis of these deep neural networks. We try to identify that what is the input noise tolerance if you are doing an adversarial attack and perturbing the input with some small noise. What is the inherent tolerance? Can I define certain bounds? Can I encode those bounds? Can I impose some kind of clipping inside the activation functions and stuff? So those kind of things that we can do, and can I derive formal guarantees on top of it? So we are looking into, for example, nowadays probabilistic model checking to explore that. So the whole idea is to get that once we output your model and the corresponding hardware and memory, it's energy efficient, it's meeting your accuracy constraint, it's resilient as well as secure. So that's where it's a multi-dimensional challenge that we try to solve. Many of these techniques, at the moment work independently, but we are trying to integrate them and see what are the implications and interdisciplinary effect, that interdependent effect that we can see. So I can skip this part. These are just some details of the structured pruning that we have done, but I just want to show you some of the important results of that. For quite some aggressive pruning, and this is a special type of pruning where we also do some kind of iterative retraining during the different cycles of that. We can see that we can even up to 90-95, like this D point, for example, we can just recover back from the accuracy loss after the retraining, and we can aggressively reduce this model. And this is one particular model. But once we have these different models, we can analyze that the impact of quantization is slightly different. So the quantization can impact adversely or aggressively. For example, if something is aggressively pruned, so the impact is much more worse compared to a non-aggressively pruned network. And of course, the reason is that you have very few number of neurons which are then critical, and any bit reduction, for example, can hurt the values. And when we do the underlying hardware approximation, these are the approximate multiply accumulate units. We have both non-self-healing and self-healing ones. We can see that aggressively compressed variants are much more sensitive to approximations. But when we use the self-healing ones, you can clearly see that up to D, we have pretty much no loss in the accuracy. When I say pretty much no loss, it could be 0.01 or 0.1%, but that's nothing in this particular case. We're still close to like 95 or more than that, accuracy in this particular case, and we can save the energy consumption, significantly in these kind of settings. So we have done these experiments for many different data sets and neural networks. So I'm just showing you, for example, even for different other type of networks, the observations are consistent, of course. For images, you can see is that the quantization impact can be pretty much similar for all these versions, and the reason is that because these neurons, for example, up to 8 bits work fine, and when you reduce the below 8 bits, then it's a little bit problematic, because these are images with color kind of settings, and that's what's very important. So having said that, we optimize our network for a given setting, and we try to squeeze as much as possible from model compression and from the approximated hardware. This is the computing part. And of course, by model compression and quantization, we also improve the memory access behavior. But we can do much more than that in memory. So there are two works that we have done. One is the work where we have developed some tool which can take your neural model, acceleration model, and it can take your deep neural network, and it can give you some analysis layer by layers that what is the reuse in the input feature map, output feature map, your weight reuse. So depending on those reuse profiles, we can identify, or we can perform a tiling of your accesses. We can define the layout in the memory, and we can optimize the access patterns. And by doing so, we have seen that from 12% to 46% savings that we can get for different type of networks. And of course, the saving can be less, saving can be more. That depends upon the data flow of that particular network and the reuse potential of that network that we have. But of course, this is without loss of any accuracy. So every single bit in energy is important to get. But what we have also done is that we have also considered multi-banked memories, and there are other special class of memories which are called sub-array level parallelism, and we have exploited that to identify an efficient mapping, and which is an guaranteed and proven optimal mapping, for deep neural networks. And in this case, we have shown that we can actually improve up to 90% of EDP, by having a much efficient mapping of the network, on these kind of architectures. So quickly moving forward, we made all these efforts to optimize the networks for convolution neural networks, but as well as also for the capsule networks. So capsule networks, when they came from the Google Brain team, they were promising that, they can learn even the pose, orientation, and other relationships between the features That's where they're employing so-called capsules, which you can think of as a 3D convolutional, representations. And then, by using the dynamic routing, you can build up the cross-coupling between different capsule layers and stuff. So in this particular case, when these networks started coming up, we saw that they have much better accuracy for very small training efforts. But of course, the training time is much bigger. So we developed the first quantization framework for those kind of things, and we studied the impact of quantization on capsule networks, and we have shown that we can reduce the memory by 6x. We also looked into some of the fast training techniques, and we implemented the regular fast training methods for the capsule layers, as well as we proposed some new ones, and have shown that we can accelerate the training by 30%. Then we also developed the first integrated NAS framework, which can give you the Pareto optimal configurations for both convolutional as well as capsule networks. So for any given specification, we can tell you that is only convolutional good, or for example, 2 layers of convolution and 3 layers of capsule, or more layers of capsule and less layers of convolution are good. So we can try to get some kind of stuff like that. So we have employed a multi-objective genetic algorithm to explore the search space along with analytical models for the fast estimation. We have demonstrated that our network configurations compared to state of the art, deep caps, for example, is one of the famous capsule network. We can offer the similar accuracy with almost half of the energy footprint and half of the memory footprint. And then we are also looking into security aspects, because there was some kind of discussions that because of the cross coupling of the features and pose and orientation, maybe they are much more robust to the adversarial attacks, but we have shown that they are not. So there is a difference between the adversarial vulnerabilities in convolutional capsule networks, but they still are highly vulnerable to different type of attacks. I quickly skip through that. We have other kind of also memory optimization stuff for the capsule networks. Another important area that I feel is very important for EdgeAI and TinyML is the neuromorphic computing, because because of the event-driven nature, has a great potential to significantly cut down the energy consumption. But they have other issues in terms of still the accuracy and learning capabilities. Spiking neural networks, for example, are excellent for unsupervised learning settings. This is a particular system that we are currently building in our lab, where we are using the dynamic vision sensors. There are also dynamic audio sensors kind of stuff. These vision sensors, are giving you only the gradient changes, for example, across different temporal frames. You can see them naturally as events. And these events can be then given to a spiking network that can be mapped on, for example, a Lohi chip to do some kind of, applications. For example, one of the applications that we have done is the background detection. So we can separate the car from a given background, which is obtained from the DVS images. And so we train this spiking neural network from scratch, and then we can showcase and map it on Intel-Lohi with much efficient way. We have also studied different parameters, impact of different mapping parameters on the resource utilization and energy consumption of that. There is still a lot of stuff to explore in this area. So we are actually working into this thing, and we are also currently talking to some of the industrial partners to identify the full scale end-to-end system use cases, and hopefully if things goes positive, then we can demonstrate some real use cases with the help of that. The biggest challenge in the spiking neural networks is really the learning rules. If your learning rules are not appropriate, the accuracy loss can be significant, but the learning rules should not be very complex. Otherwise, we lose all the benefits of energy savings that we get. So we are actively looking into different optimizations. So there is a couple of frameworks that we have released and open source now, where we are looking into different dimensions of reducing, for example, the energy consumption. For example, instead of having multiple dependencies, we can have lateral inhibition. Instead of having a separate inhibition, like side tree layers, we can have lateral inhibition, cutting down completely one layer and then saving a lot of energy. We can do those kind of optimizations to further reduce memory. We can exploit voltage overscaling in spiking neural networks. We can also understand different type of plasticity models in unsupervised control learning. We can identify what are the spurious weight updates and what are the ranges of membrane potentials which can lead to energy efficiency, and we can identify an optimal set of parameters to further cut down the energy. So for example, this work can cut down the energy by half while still preserving the learning capabilities. And in some cases, we can even online learn to give improved performance. Again, quantization for spiking neural networks is an important aspect that we have explored recently. I quickly go through that. Security of spiking networks is again another thing. Again, there are earlier people community thought that maybe spiking networks can be much more robust because they have a higher biological plausibility. But community has shown that there are new types of attacks that can be done on spiking networks, and we have done also a couple of attacks. Again, they are different from convolutional neural networks, but there are different type of attacks. And so in one of the works, we have studied the impact of different parameters of a spiking neural network, like the voltage threshold, the time window, the time to update the parameters, and those kind of stuff that we have seen that how they can affect the robustness. One of the first attacks on the DVS cameras that we have demonstrated for autonomous vehicle, which was shown at the IROS conference in the robotic community, was this was the one of the first adversarial attacks that we have shown that we can introduce some imperceptible perturbations in DVS camera, and that can also, for example, trick your neuromorphic hardware and spiking. So we are looking into different types of these attacks. So towards the end, I want to present one of the another use cases that we are working with some healthcare partners. So we have deployed, these kind of principles in specifically for biosignal processing. I just quickly skip through that, and I want to show you this: the neural architecture search framework for hardware constraints healthcare DNNs. This is a very extensive framework that we have developed. It can retrain a network and do a model compression, as well as it can do the neural architecture search, again using genetic algorithms, which is our expertise. So what we can do is that we can output a model which has 53x reduction in the hardware overhead with very minimal quality loss. So quality loss can be an input constraint. So we can give even 0% loss, and then we can get, for example, 20x reduction in the hardware. The end use case that we are currently building is a part of a large-scale EU project, which is together with different industrial partners, specifically with, for example, one of the healthcare partners we are working. We are developing a handheld ultrasound device which can monitor for example, the state of the fetus. There are a lot of challenges. We acquire the data. We do some kind of segmentation of this data using deep neural networks. Like UNet kind of models. We are building our own neural models. We are building our own data sets together with the industry partners. And then our end goal is to build a very small scale device which has a small, either an embedded GPU or a small FPGA with a tiny DNN into this, which can not only do the segmentation but also can predict the state of the fetus, so that you can monitor the health of the baby in early stages, and then can reduce the chances of miscarriages or health anomalies for the fetus. This is done together with Philips Healthcare, and done mostly the work is done in my group in the TGVN. So having said that, the future research directions are a lot. From my point of view, when we talk from the technology perspective, there is a lot to be done for the in-memory computing, near-memory computing, and of course, using the emerging technologies, where there's different ways of using the emerging technologies. Emerging technologies have their own issues, like different sources of noises can come there. Can you incorporate those specific features of in-memory, for example, in the design flow of a neural network? That's one thing. Other thing that I personally feel is, a lot of times we are working only in deep neural network. Of course, there is a lot of conventional machine learning models that can come, but if you look at this, 2-3 areas of machine learning models are getting mainstream. So somehow this dependency that first a machine learning model comes and then we try to fit it on the device, this has to break, and we need to come up with a complete hardware software co-design approach where we can, for example, also consider the device constraints, the system constraints, to see that what kind of models would eventually fit the best to our requirements. Optimization frameworks for all different type of system constraints. This is important. Most of the work you will see are area efficiency or energy efficiency, but we need a multi-objective framework which can give me a resilient, robust, secure, highly energy efficient, intelligent system, TinyML EdgeAI system, where I can also give you the formal guarantees and bounds, and that can be certifiable. So that should be the end goal for the whole community. Again, we need novel techniques for training and learning. But I want to come to one of the points, so I'll just quickly skip through that. I want to come to this point. There is a large initiative on lifelong learning. So the modern systems, when we are going to deploy them in, for example, predictive maintenance in some cyber physical factory or industry 4.0, or we're going to put them in small, tiny robots like, bee robots, or, really the nano robots kind of stuff. Many of these systems, cannot be trained one time based on your data sets. They might be going through some unforeseen situations. So they need to have a capability of lifelong learning. But we already see that inference is a big challenge on these kind of devices. So how to enable lifelong learning on these kind of TinyML and EdgeAI devices? This is a gigantic challenge from my point of view. And this requires a completely new ways of thinking, and I think there is a lot to be explored here, and we might need to explore some new like parametric model. We might need some hybrid training inference models kind of, and frameworks for that. So that's where I close or complete my talk. In general, there is a statement that came from the program manager. In a few years, much of what we consider AI today won't be considered AI without lifelong learning. I would like to thank my team. The work that I've shown you is a work by a lot of PhD students and masters and bachelor students. And of course, this list is not up to date. There are a lot of other people who are currently working on the thing. And I would like to thank different centers at NYU Abu Dhabi, and my group at TU Vienna, and all the funding partners for supporting this thing. And I'm open to your questions now, so as long as you want. So I'm here, and thank you very much.
Hey, thank you so much, Shafiq. Really appreciate your great talk this morning. So we've got some good questions from the audience, and I'd encourage, if you've been watching the talk but didn't necessarily have your own question, still jump into the Q&A tool and upvote any questions that you think are interesting. So our first one at the top of the list here is about ensemble models for TinyML. So the question is, I was wondering your opinion regarding replacing one big model of massive TinyML models by averaging the outputs, for example, in an ensemble form from a lot of smaller TinyML models.
Well, this is, as I said, this is another way of looking at the problem. So there are different learning problems. If you have a distributed learning problem, you might be able to look at that. If you can break your learning problem into small networks, and then you can build a team of tiny DNNs. That's again a great way to look at the thing. Would this be an optimal way to look at the problem? I think the community still has to demonstrate that for multiple different use cases. My take on this is that this is a use case to use case specific, solution for that.
Okay, thank you. All right, next question up from Bill. He says, you advocate numerous steps for improving accuracy and speed and making other improvements to this process of training and running models. Are these steps and the results documented somewhere so that practitioners can access?
Exactly. Yeah. So if you would have noticed, I was giving some publication pointers, at every of the slides. I can just quickly go through one example, and you will see that. So, for example, look at this. So there is like DAC 21 stuff. So what I can do is that I can put a list of publications at the end of the presentation, and I can update Daniel and Olga with all the set of publications so that you can have a look at those papers. They are published. Many of these frameworks are even open source. And this you can find that which frameworks. So for example, this CAPSNAS is like an open source framework. Similarly, the other frameworks that we have worked on, healthcare, and if there is something which is not open source yet, which means we are working on on refining that and polishing it, so that it can be usable by the other community members. Because once we open source, we also provide really some help for people to reproduce the same results under the same settings, same configurations. So of course, these are all published results. That's why I was presenting. Everything is open at the moment. Yeah.
Fantastic, thank you. And just for everybody, the slides, we will be posting them on the forum after the talk tomorrow, and the video will be also posted to YouTube tomorrow, so you can dig in and find the particular content you want to read more into. Next question up, is there spiking neural network hardware in the market right now? Intel's chip doesn't seem to be available publicly.
Yes, so I mean, you are right. So there is, for example, of course, IBM True North came earlier. Intel Lohi is also a research platform. We also have partial access, through cloud and under the contract with Juliana even. But currently, I am working with, some of the. Recently have talked with some of the industrial partners, and there is a growing interest of building up, these neuromorphic chips for, really practical products. The issue they are very consistent. Spiking network community and neuromorphic community still have to prove that they can beat, in terms of accuracy. They are great for a very small set of tasks, but really beating them, the counterpart is still a challenge. I see there is a great potential just because of their mathematical foundations, just because of their logical reasoning and capabilities of unsupervised learning. At some point in time, you might even see that both DNN and SNN might coexist in a real model because both have their pros and cons. I don't see them, one replacing the other. But yes, having an access to neuromorphic hardware is challenging at the moment.
That's a very good example of Sarah Hooker's hardware lottery principle, that the hardware that we happen to have access to leads the direction of research more than the other way around.
Yeah.
So next question up, what's your opinion regarding the use of early exits for deep learning models for energy efficiency?
Early exits? What does early exit mean? You mean early termination of the processing, or what?
Jumping out at a layer prior to the end, depending on some kind of metric.
People are, I don't know. Frankly speaking, this again highly depends upon the input data that you are, feeding in. The problem is really, as I said, is really not on, how much computation you want to save. The problem is really about also the guarantees in a real world setting. You can early exit, but can you still, guarantee me that the result that you get is acceptable for the final system or not? Who will derive these bounds and guarantees? Someone has to do it at design time. There is no human in the loop sitting, at the moment. Although people are talking about a human in the loop kind of things also, but I think these are nice ideas, but they have their risk and practicability issues in the real world setting when you come up with verifiability and bounded certifications and things like that.
All right, we've got a question from Stacy. Am I correct in thinking that chips performing inference are currently poor at handling the needs for lifelong learning? And could you talk a bit more on that?
My experience is that, I would not say they are poor. I would say that they are not designed for that task. I would say that. You might still say that I can implement a lifelong learning algorithm on an embedded GPU like Jetson Nano, and you might get some performance improvement compared to a regular CPU-based system. But they may not be optimal, for that kind of principle. There is also algorithms which are still missing from the community, because the content learning community has solved these problems from very different perspective, like open world detection problems and those kind of things. They were never subjected to the constraints that we see now in the TinyML and EdgeAI community, and they were never subjected to the security issues that they were. So I personally feel that if you today implement a lifelong learning algorithm on today's embedded GPU, or you will get some acceleration, but those devices are not optimally designed for those kind of things. That's my take on that.
All right, so probably our last question due to time considerations from Mohammad Usman. What are your views about in-network computing for learning and inference?
In-network computing, I mean, I may not be, aware of this term. What's that? Can someone explain this? You mean in-network computing or in-memory computing or what?
Yeah, I guess we don't have time for an elaboration.
Okay.
So I can jump to a different question.
Drop me an email and we can have a discussion on that. Just.
Okay, here's a good one. I'm very keen on this question. What is meant by conventional machine learning, and how does that fundamentally differ from deep learning in terms of applicability for TinyML?
Yeah. You see that the problem is nowadays everyone, when we talk about doing machine learning, they all talk about deep convolutional neural networks, and they think this is the solution to every problem. This is the solution to many problems, but not every problem. So you might have, for example, you don't have a lot of training data sets. So you might see that maybe support vector machines could be still good. So when we talk about conventional machine learning, there are a lot of other algorithms like decision trees, support vector machines, those kind of algorithms. I would even take one step back, and I would say that it's not only machine learning but regular statistical inference toolbox. Whatever statistical inference toolbox that we had can still solve a lot of our problems to derive predictions, to derive models. Even, I mean, so machine learning currently what we see is a complete black box model, but there are so many gray box modeling techniques, and those could be beneficial for many things. And even we can have, for example, because the benefit that we get from deep networks is identifying or expanding the set of features, because earlier we were relying on human generated features. Now we have automatically generated features. So you can use a deep learning network to, for example, generate features if we can understand them. I am not going into the explainability issues at the moment, but then you still have other toolboxes available or algorithms available to mine your problem, to derive predictions. We know that time series prediction is again another complex problem where the trend is going towards deeper and deeper LSTMs, attention-based networks, all those kind of stuff. But they are becoming more and more complex. And if I want to have a time series analysis on my very small, tiny band, then I'm in a deep trouble for that. So I think that like deep learning was kind of, resumed after the breakthrough of the computing power and the data set. There might be other, models from the traditional machine learning. And one step ahead, maybe even AI. AI community is much bigger than only machine learning. So we might be able to find some more strong mathematical foundations to explore, or at least revise based on our current system settings. That's what I meant with that.
Okay, fantastic. Well, I think we're just up on time, so I'm going to go through our outro slides. But again, thank you so much, Shafiq, for your contribution today. And thank you to all of our viewers who submitted questions and tuned in for this session. Stick with me for the next few slides.
Thanks for inviting us.
So hopefully you saw the 5-question poll pop up during the talk. Please take a moment to complete that, just to rate how our session was today. And then once again, huge thank you to our strategic partners for making this possible. Please contact Olga at tinyml.org if you'd like to be a sponsor in the future. So I'm going to go through a few of our partners here with some more detailed information. So ARM provide the software and hardware foundation for TinyML. Edge Impulse, which is where I work, we're the leading Edge ML platform. You can take a look at edgeimpulse.com. Qualcomm AI Research are advancing AI research to make efficient AI ubiquitous. Okay, here we go. Sentient provide end-to-end deep learning solutions for TinyML and EdgeAI. Here are our platinum strategic partners. DeepLight use AI to make other AI faster, smaller, and more power efficient. ClickerTech provide global IoT solutions. Reality AI allows you to add advanced sensing to your product with EdgeAI and TinyML. Renesas provide a broad and scalable edge computing portfolio. And here are our gold strategic partners: PhotoHub, Maxim Integrated, who are enabling edge intelligence, Latent AI, who are providing adaptive AI for the intelligent edge, Micro AI, NXP, Seed, the IoT hardware enabler, SenseML, who build smart IoT sensor devices from data, ST, SynSense, who build sensing and inference hardware for ultra-low power embedded mobile and edge devices. And then thank you to our silver strategic partners, Aeon Devices, Emza, Greenwaves Technologies, Gravetti Incorporated, HOTG, Imagimob, Itemis, Prophecy, Kixo, Rexen, SAP, and Stream Analyze. As I mentioned earlier, our next talk is coming up on Tuesday, February the 8th. That's Stefano Cadario, Director of Product Management at the IoT Group of ARM. And his topic is going to be Get Ahead of the Curve, Develop Software in the Cloud for the Ethos U55 and Cortex M55 processors. Should be very exciting. The webcast is going to start at 8 a.m. Pacific, same time as today. And if you have a topic you would like to talk about, we'd love to hear from you. So please contact talks@tinyml.org if you're interested in presenting. So that's it from us. Thank you so much to everybody for joining in, and to Shafiq for being our excellent presenter today. I hope you have a great rest of your day.